Hello, welcome to Lancaster Hi-Fi. This video is going to be the first in a series on the construction, the build of a DG-SE1. That is a Dave Gillespie single-ended Mark I tube amplifier. I've built a few of these, and I have varying amounts of footage from various builds. Originally, I was going to make this series entirely based on a build that I did last summer, that is in July and August 2022. Hello and welcome to the Lancaster Hi-Fi channel. I am Stephen Lancaster. However, my footage from that build isn't quite comprehensive enough, and in order to make the different parts of the video series able to stand on their own, I'm going to need to combine footage from some different builds. Hello, welcome to the Lancaster Hi-Fi YouTube channel. I'm working on a build of a DG-SE1. Specifically, in this video, I'll go over the circuit diagram for the DG-SE1 and specifically address the different things that I needed to do in order to make it work with the AMP 196 chassis that I used to make the build last summer. Part 2 will cover the layout and planning of the build itself on paper. Part 3 will address the chassis preparation and modification, holes, finish, etc., and the installation of the major components such as the output transformers, the power transformer, the power input module, and so on. That will need to use some footage from a build that's actually still underway. Past part 3, I'm not entirely sure what the theme is going to be for each. I'm thinking that part 4 will deal with the overall wiring and installation of the minor components, capacitors, resistors, etc. inside the chassis. And then part 5 will cover the testing of the amplifier and perhaps some of the modifications that arise as necessary from the testing. Again, I'm hoping that each video will be useful and entertaining on its own, because it's a bit of a chore to sort through all this footage and figure out exactly how to put it together. So I hope you'll bear with me. I hope it's going to be good, and I think it will be good. I'm going to try to make it good, and I hope you'll follow. So, cheers and enjoy. If you haven't already, press the like button, subscribe, make a comment. Might make a comment later though. I'm building this single-ended tube amp based on 6BQ5 or EL84 tubes for the outputs and 12AX7 triode tube on the inputs. This is Dave Gillespie's schematic for what has been termed by others and later referred to by Dave as the DG-SE1. As you can see, it says it's a modified Magnavox 8604-00. This is the first schematic that I'm working from, but the amp I'm building can't follow this schematic exactly. Let's look at what this schematic shows. So we've got an input stage, which is half of a 12AX7/6EU7. The 6EU7 is supposed to be electrically identical to the 12AX7, although they have different pin outs. So that's why this schematic doesn't show any pin numbers on this triode here. So we've got the input coming in here. We've got a grid leak resistor 470K, which is a pretty common value. Another common value might be 1 mega ohm. We've got a 10K stopper resistor coming into the grid. So whatever input comes into the grid is amplified by this circuit. We've got a voltage of 255 volts here through a 470K resistor to the plate. In a typical transistor diagram, this voltage would be shown up at the top. The transistor equivalent of this would be a common emitter but we could call this I think they called this a common cathode. That is, the cathode here is grounded, but not exactly grounded. It's got an 820 ohm resistor here. And then we're pulling off the signal below this resistor. That goes through this blocking capacitor, a DC blocking capacitor, to the power stage. The power stage is a pentode, 6BQ5, otherwise known as an EL84. This is a pretty straightforward circuit as pentodes go, although pentodes are a bit more complicated than triodes. A triode circuit is generally, as we can see here, very similar to a transistor circuit. However, a pentode has a little bit more complicatedness going on. I'll get to that. So the power source or voltage source, the B plus here, is shown as 265 volts. And that is going through the primary of the output transformer, which essentially serves as the sort of bias resistor similar in function to this 470K resistor here. We're pulling the signal out of what current is going through this coil here. So that 265 volts drops to 255 volts at the plate. And where it's similar to a triode circuit, it's a common cathode type circuit where we've got a resistor here shown as a trimming potentiometer and a fixed value resistor bypassed by a capacitor. So that's pretty common design for transistors and also for tubes. And it gets a little bit more complicated for a pentode, where the pentode has this screen grid here, which in this case is at 255 volts, which is the same voltage as at the plate. What we can also see here is that this test point is at 5.85 volts. That means that the cathode here is at a voltage a little bit higher than 5.85 volts, depending on where this 50 ohm trim pot is set. We've got a little less than 250 volts potential between the plate and the cathode. Got the grid leak resistor here, 470K. 470K resistors are ubiquitous in tube circuits, it would seem. So that's the basic design. We've got two gain stages here and here. And this one is mostly a voltage gain. This one at the plate is a large voltage gain, but the transformer turns it into essentially a current gain stage. On the secondary of the output transformer, the ground side is grounded, and on the signal side, we've got first a Zobel network. A Zobel network is simply a resistor and a capacitor in series, and these are typical values that you find in Zobel networks. So 47 ohm resistor and a 0.1 microfarad capacitor. Zobel networks confer greater stability to the circuit, and that's about all I can say about them, but they're pretty common in both transistor and tube circuits. And then we've got this feedback going to the cathode. If this were, say, an op-amp circuit, we would have positive and negative inputs, and this is similar to, as we would have with an op-amp circuit, the feedback going to the negative terminal of the op-amp. We've got a 10K resistor, and that 10K resistor is bypassed by a 300 picofarad capacitor. The 10K resistor determines how much of the output we're sacrificing for linearity in the circuit. In this case, it's labeled as 17 dB NFB, or negative feedback. And the 300 picofarad capacitor helps determine the frequencies at which the feedback is stronger or weaker. And in particular, we generally want to have the feedback be less strong at the lowest frequencies, because that's where the output transformer tends to produce more of a phase shift. If we get too much feedback at frequencies that are shifted in phase too much, then we get instability. And that can occur both at very high frequencies and at very low frequencies. So at very low frequencies, you would get what's called motorboating, sometimes a 1 to 10 hertz oscillation. And in the high frequencies, typically you'd see 100 kilohertz instability. And either of those things are bad. The 100 kilohertz will tend to rob power and heat up your tweeter. The 1 to 10 hertz will sometimes produce sort of a popping sound in your woofer because the motorboating is often a pop every second or 10 times a second. That is 1 hertz to 10 hertz. So that's the amplifier circuit, and this schematic only shows one channel. In the actual amplifier, there'd be 2 identical channels. Down here is the power supply. We've got AC power coming in on the primary of the transformer. So we've got 3 secondary coils shown here. In this case, the rectifier tube is a 6CA4. The 6 simply tells us that this uses a 6-volt heater supply. So it will run off the same heater supply as the other tubes, as the 12AX7 or 6EU7. The 12AX7 can run on a 12-volt or a 6-volt heater supply. The 6BQ5 runs on a 6-volt heater supply. So in this case, the rectifier runs off that 6-volt heater supply. More commonly, rectifiers use a separate 5-volt supply. Now this transformer has 2 6-volt secondaries. This second 6-volt supply would have provided power to the heaters in the tuner. There is no tuner in this system, so what's going on here? This is a buck modification. In the past, AC power in the United States was lower than it is now. Typically in the, say, 1960 to 1970-ish, AC power was at 117 volts RMS, and now it's more like 122 volts RMS. So that difference in AC voltage can be a problem for the heater supplies. Your tubes will run just fine without this buck modification, but it's likely that the voltage will be too high for the heaters. And they'll run okay, but your tubes will burn out quickly. So this modification here essentially adds turns to the primary so that the secondary voltages here are lower. And in this case, it comes out nearly perfectly that the 6-volt supply gets back down to a 6-volt supply rather than, say, a 7-volt supply. And the B plus is derived from this secondary here, which is a center-tapped coil. So we go through the rectifier. So this would be essentially 120 hertz hump signal that's smoothed somewhat by this capacitor, and then it goes through this filter choke, which filters out that 120 hertz and gives us nearly DC at the B plus here, 265 volts, where we've got another capacitor for smoothing. This choke also gives us 56 ohms, which drops the voltage a bit from 270 volts to 265. Then we've got a second dropping resistor here, this 820 ohm 1 watt resistor, which drops the voltage again to 255 volts, which is the voltage source for the screen and for the input stage. The heaters are not shown on this diagram, that these are the heater voltages. We go through a 100 ohm resistor on both sides of that, and we pin the center of the AC voltage to pin 3 of 16BQ5, pin 3 being the cathode. So that essentially takes this off of ground, which eliminates the possibility of a ground loop hum. This trim pod is labeled bias, and we see TP for test point. This shows that this test point should be at 5.85 volts. 5.85 volts across 120 ohms gives us about 49 milliamps current total through this tube. That's current that comes through both the screen grid and the plate. Most of it will be through the plate. So this is a Class A amplifier. It's dissipating quite a lot of heat. It's constantly sinking 50 plus 50 milliamps, so 100 milliamps over 250 volts. 100 milliamps is 0.1 amps times 250 volts is 25 watts. If you had a 25 watt light bulb, it would get pretty hot, maybe too hot to touch. In this case, that heat is dissipated across a big steel chassis, and so the tubes are too hot to touch, but the chassis is just kind of hot, not too hot to touch usually. So that's the basic circuit for the 8600 series. Specifically in this case, Dave was using an 8604-00. I'm using an amp 196-00. What are the differences? Well, it uses a 12AX7 instead of a 6EU7. That's fine. It also uses a 6BQ5, so we're good there. Where it starts to really differ is in this rectifier tube. The 196-00 uses a 5U4GB, or just 5U4, rather than a 6CA4. And in particular, the combination of the power transformer on my 196-00 and that 5U4 rectifier tube produces a voltage much higher than this 270 volts. It produces more like 315 volts, and that is rather high for this circuit. So some things need to be modified. Let's look at ways to modify it. Here's a diagram showing one potential modification for the 196-00. So this is labeled Magnavox amp 196-00 with DG-SE modifications. We see here that there is now another secondary coil up here, which is the 5 volt supply for the 5U4GB. GB just stands for glass bottle. We've similarly got the buck modification here. And then here's the 6 volt supply for all of the tubes except for the rectifier. In this case, it shows the original hum balance potentiometer. And this is the most straightforward modification of the original DG-SE mods. We've got an extra dropping resistor here for the B+. Rather than just the choke, which dropped us from 270 volts to 265 volts, this shows that we have 285 volts off of the rectifier. It's dropped by the 56 ohm choke and a second 150 ohm resistor to get us the 265 volt B+ that is called for in the original design. And then a second 820 ohm resistor as before to get us to 255. This 285 volts is substantially lower than I measured on my amplifier, on my 196-00. So apparently different 196-00s had different transformers. I measured about 325 volts at this point, so quite a bit higher than this 285. I could still use a mod very similar to this and simply use a larger resistor here to drop the voltage further in order to get down to 265 volts. One more noteworthy difference in this schematic, and that is that this employs a 1K grid stopper resistor, and that's to mitigate any potential for instability in this particular design. I need to make a decision on how I'm going to do this power supply. So the first option, and I think the one I'm going to go with, is this sort of option. Not exactly, but we simply add a dropping resistor here to get us down to the 265 volt B+ that the design calls for. The other option is this sort of option. We go with the high B1, we go with the low B3. In this case, we add something like 3.9K and 4.2K resistors. In the other case, we need a relatively low value resistor. In this case, this says 150 ohms, but it's coming down from 285. I've got something like 325, so I need a larger resistor value here. And my calculations say I need 582, thereabouts. But once I drop down to that, now this says 10 watt, and my calculations say that dropping as much voltage as I need I need at least 7 watts there. And we usually overspec these resistors. But if I get this down to 265, then everything else goes according to the design, the original design. Then I got an 820 watt or 820 ohm resistor here, and so on. I'm less sure of this scheme. I don't know if it's actually applicable to my case. So I'm inclined to go with the other scheme, this one, which gets me right into the design simply by brute forcing dropping voltage here. This is my as-built schematic for the DG-SE1 built on the AMP196-00 chassis. Just a couple of things that were left hanging earlier. So here's the power supply. So here's that 550 ohm resistor that I was talking about, and 820 ohm resistor. I want to say that actually is supposed to be 1.5K. So we've got a 266 volt supply. That's the one going to the plate through the output transformer. 251 volt supply, which is going to the screen of the output stage pentode and through this 470K resistor to the plate of the input stage. One thing I can point out here is this 150K resistor here helps bootstrap this voltage right here to be 1.45 volts and keep that stable. And one more change, I think I've mentioned this before, but so here on the cathode network for the output stage, I've got a 100 ohm sense resistor and a 100 ohm trim pot. So rather than 5.85 volts on the test point, it should be 4.87. One change that's not on here is a couple of times now I've added a 220 microfarad capacitor here to reduce the hum. It doesn't make the hum go away completely, but it does cut it back quite a bit. My first DG-SE1, you can see that extra capacitor behind the metal can there. So I'm going to mention one variation on the DG-SE circuit. Here you can see most of one channel. Here's the input stage, the output stage. Forget that it's labeled 6V6 GT. That's just me being lazy about the model. It should be labeled 6BQ5, as you can see there. The thing I wanted to point out is I do have one version of this amplifier, in fact, that one, that has a couple of switches on it. I've represented those switches on this circuit diagram with a couple of jumpers. So, as it's set up right now, here's the switch that says pentode and triode, and this one says NFB and out. Okay, so right now, the jumper's on the pentode, so the screen is connected to the 255 volt supply, and the feedback network is connected. If I flip those switches up, then I remove the screen from the 255 volt supply and connect it directly to the plate. So that's triode wired. And if I flip up the other switch from NFB to out, then I remove that jumper and the feedback network is disconnected. So that's how you can turn this amp into an SET amp if you so desire. In my subsequent builds, I haven't wired it that way, in part because the switches are kind of hazardous to use. Well, not hazardous. It's just they're awfully tempting on the front panel to just switch back and forth to see how it sounds. Problem is, if you do that, those switches aren't rated to switch that kind of DC voltage, and you get arcing and you ruin the switches right away. Still, it was nice before I realized that that's what I was doing by switching back and forth, to be able to compare and contrast so quickly like that. Well, that's the end of part 1. Next time I'll be going through the design on paper. If you enjoyed the video, please give it a like. Give me a subscribe too, that'd be awesome. Hope to talk to you soon. Have a great day.